Today, we're taking a look at one of Albert Einstein's most famous Nobel Prize-winning ideas. But what if it was only half the story? What if it has a mysterious, mirror-image twin living in the world of antimatter? And that's really the big question here. What if the photoelectric effect, a cornerstone idea that literally kicked off the quantum revolution, is missing something? What happens when you take out the normal matter and swap in antimatter? So, before we can get to the new stuff, we've got to start with the original. Let's rewind all the way back to 1905. A young patent clerk named Albert Einstein comes up with this totally radical idea that's going to change how we think about light itself. He called it the photoelectric effect. And the concept is actually, beautifully simple. You shine a light on a piece of metal, and if that light is energetic enough, bam, it can actually knock electrons clean out of their atoms. This proved light wasn't just some wave. It was acting like a particle, a little packet of energy he called a photon. And this is the super elegant equation that sums it all up. The energy of that incoming photon, h nu, has to be bigger than what's called the work function, which is phi. You can kind of think of that like an exit fee the electron has to pay to leave the metal. Whatever energy is left over becomes the electron's kinetic energy, Ke as it zips away. Simple, powerful, and definitely Nobel Prize worthy. But here's the thing about our universe. It seems to love symmetry. For just about every particle of matter, there's an antiparticle. And this one simple fact just adds this whole fascinating new twist to Einstein's classic idea. So fast forward to 1928, when a physicist named Paul Dirac predicted the existence of the electron's perfect mirror twin, the positron. And right here, you can see just how perfect that symmetry is. A positron is basically identical to an electron in almost every way. Same mass, same spin, but with one huge difference. Its charge is positive. It really is the electron's antimatter doppelganger. So this leads to the big puzzle, right? If a positron is just a mirror image of an electron, shouldn't we be able to just, swap them out in Einstein's equation and call it a day? Get a positronic photoelectric effect? Well, it turns out the world of antimatter doesn't quite play by the same set of rules. And this is where our deep dive really begins, because when you try to figure out what happens with a positron, you slam into some seriously exotic and frankly dangerous complications that just don't exist for our good old reliable electron. You've got three major hurdles. First, and this is a big one, the annihilation problem. When a positron touches an electron, they both just vanish in a burst of energy. Game over. Second, sometimes right before they annihilate, they can form this bizarre, super fragile atom called positronium. And third, there's a really deep question. Is the universe's matter-antimatter symmetry, what physicists call CPT symmetry, absolutely perfect? Any new theory has to deal with all three of these. So, how on earth do you build an equation to juggle all of that? Well, let's follow the logic from the source paper by Reza Kronkanha and actually construct this new formula, piece by piece. We're going to start with the simplest guess we can make. Then, we'll add in layers of complexity to handle the weird physics of the positron, looking for any hidden cracks in our understanding. And finally, we have to deal with that constant, looming threat of annihilation. Okay, step one is the most logical first move. We just create that mirror version we talked about. We swap the electron's kinetic energy for the positrons, and we swap the work function for a new, hypothetical, positronic work function. It's a really clean start, but it's just not the whole picture. Next up, we have to deal with that positronium thing. See, if a positron gets briefly trapped with an electron in that fragile atom, the incoming photon suddenly has a second job. It doesn't just have to eject the positron, it first has to pay the energy cost to break that bond. So we've got to add a new term for it. Now, this part is super cool. What if that mirror between matter and antimatter isn't perfect? What if it has a tiny crack in it? To test for that, we add a small correction factor. If this term, this delta CPT, turns out to be anything other than 0 in an experiment, it would be a huge deal. It would point to brand new physics, stuff beyond everything we know right now. And finally, we come to the most dramatic difference. A positron trying to escape a material is basically flying through a minefield of electrons. There is a very, very real chance it's going to annihilate before it ever gets out. So we have to subtract a term that accounts for all the energy that could be lost in that catastrophic event. And there it is. You put all those pieces together and you get the Einstein-positron extended photoelectric equation. You can still see Einstein's original idea kind of buried in there, but now it's been expanded to account for the unique, wild physics of antimatter, that fragile positronium state, the test for hidden symmetries, and of course, the ever-present danger of annihilation. So let's just break that down one more time. The energy from the photon now has to do a lot more work. It has to pay that exit fee, give the positron its speed, and maybe even break up a positronium bond. Then we have our special term to hunt for new physics, and finally, we subtract any energy that might be lost to annihilation. Every single piece tells a part of the positron's really perilous journey. So we have this new, kind of complicated equation, but so what? Why does building a theoretical tool like this actually matter for the future of physics? What can we do with it? Well, this is where it gets really interesting, because this isn't just some thought experiment. It's a practical roadmap. By designing experiments to actually measure each of these new terms, scientists could test that fundamental CPT symmetry, get a better handle on things like antihydrogen, and hunt for physics beyond our current standard model. It literally lays the groundwork for future technologies we can't even build yet. And ultimately, this paper isn't just providing an answer, it's an invitation. The author really frames it as a call to action, a challenge to the scientific community to start designing the experiments that are going to explore this whole new frontier, where light, matter, and antimatter all meet. And that leaves us with one final, kind of mind-bending thought. We started with one of the most established, most elegant rules in all of physics. And we found out it might have this hidden, much more complex antimatter twin. It just makes you wonder, what other fundamental laws of our universe have a secret side just waiting to be discovered?